All right, so can everyone see my screen? All right, good. So I'm going to borrow Andres's analogy and say that what I'm about to do for you is dance. And I'm about to dance the dance that I know the best. And if you were to watch me dance your dances, I would be super awkward. But this is the dance that I can do. And so I'm really happy to be able to share with you today a bit of the nuance in the problem that we're going to try to solve in this program, a bit of the history that leads into it, and a bit of the open-ended, unsolved problems that we're going to try to address. And I like to start stories whenever I can with Galileo. And so we're gonna go way back, and we're gonna say that the first observations of spots on stars actually came from, let me put in another caveat. The first observation of spots on stars using a telescope that was recorded in human history was in 1612, when Galileo took observations of the sun through a telescope, where he projected the image of the sun onto a piece of paper, and then he traced out the spots that he saw in the sun. And he did this over a few months, and what he saw is what you see on your screen. He saw that there were dark spots that emerge and decay predominantly at 2 active latitudes on the surface of the sun. This observation was interesting from an Aristotelian philosophical perspective, because they thought the sun was a perfect sphere and marks on the perfect sphere was a problem. But for me, this is where the exciting part starts, because there's so much physics going on in these dark spots. What kind of physics is there? What can we talk about? Well, there's spot latitudes in the image that I showed you before, which is to say that the spots tend to appear at 2 regions on the surface, and the spots are emerging and decaying. They come and they go on a timescale of about a month to a few weeks. And that information is encoded in brightness measurements of stars like the sun. And so here's what the sun actually looks like if you were to take an image of the sun every 8 hours for several years. And you can see that the sun is rotating, the sun has spots. It looks just like Galileo's image, except it's much fancier because this is a space telescope that's taking images of the sun continuously. And then in the bottom right, we have an even fancier image of the sun, which is taken at a different wavelength, blue of the optical, so that you can see some of the active regions on the surface of the star highlighted in a different way because of the way the gas is emitting light. And you can see that the number of spots on the sun is changing as a function of time. You can see that some spots last 1 full stellar rotation, but others don't. And you can see that those spots occur at the 2 active latitudes that I pointed out earlier. And the number of spots actually increases and decreases on an 11-year cycle. And that looks something like this. This is our favorite way of displaying the activity cycle of the sun. This is called a butterfly diagram, because if you tilt your head to the left, it looks a bit like a bunch of butterflies. And what we have are I see a bunch of heads tilted to the left. I love it. What we have on the color axis is the number of star spots within a bin of latitude. And on the x-axis, we have time. On the vertical axis, we have latitude bins. And so what we're doing is we're watching as the number of star spots changes as a function of latitude and time. And you can see that spots tend to emerge first. Let's pick 1952. Right in the middle is our example. If we start at 1952, you'll see that star spots start emerging at latitudes near plus or minus 40 degrees. And then as we work our way into 1958, the spots are appearing at roughly 15 degrees. And then as we work our way into 1963, the spots have started to emerge near the equator before the spots basically disappear and the cycle starts again. This is what we call the solar cycle. We believe that this kind of cycle probably happens on other stars as well. And we have some observations to show that other stars also have cycles, but it turns out to be notoriously hard to measure in practice. Now, what is the physics that we actually care about that makes this all interesting to me? Star spots are the outward manifestation of something that's happening deep within the solar interior. This is a model of the sun where the wires that you see in the image are representations of the magnetic field within the sun. And we've peeled away the outer layer of the sun, and you can see that at the base of the convective zone in the stellar atmosphere, there are these thin loops of magnetic fields that are very strong. And those strong magnetic fields occasionally become buoyant and then rise through the surface, where we see them emerge as star spots or sunspots on the sun in this example. So please call me out if I'm ever using sunspots or star spots backwards. I'll do that a lot. Or probably just say star spots all the time, because that's all I think about. And what you can see is that there's a cycle happening, that the band of active latitudes is moving throughout the cycle, and that gives rise to the change in the number of spots that we observe. Now, let's talk about what we actually observe. So in light curves, we have two main properties that are easy to measure. Let's look at a real light curve and see what they look like. This is the test light curve of a star called AU-MIC. AU-MIC is an M1 star, so this is not a star like the sun. And that's interesting because M stars have more activity than sun-like stars do. And so you can see that reflected in this light curve, because the vertical axis here is the total brightness of the star, and the horizontal is a function of time in units of days. And you can see that the brightness of the star is changing by about 5% on 4.8 day timescales. The sun, if it changed by 5%, we would have variations in weather due to the sun, right? Like that would be like, the sun's actually brighter right now. That would be different. We don't have anything like that. And so this star is much more extreme than the sun's spots. We know very little about what these spots are like. We don't know if they're bright spots or dark spots, for example. And we don't know how many of them there are. I'm working on a paper on this system, which I think is really neat. I'd be happy to answer your questions about it later. The blue here is a model which just has 3 spots rotating into and out of view as the star spins. And the black data are from TESS, which is a planet hunting mission.
Is it common that it looks kind of more or less periodic, like that it has a specific shape, even though, okay.
Yeah, so something we're going to see within this presentation is that sometimes they're very stable and periodic, like this one, but other times the periodicity lasts for as long as one rotation. And that makes it much harder to detect the periodicity, because then the periodic thing you're looking for just lasts one cycle, and then it's really challenging to measure. So that's something I'm going to come back to. Thank you for that question. I want to address something that's implicitly happening in all of our observations of real stars that most astronomers will never bring up, which is that we don't generally know the orientation of the stars that we're looking at. Some of them have their rotational poles pointed at us, like the star on the top row, and some stars have their rotational poles in the plane of the sky, so like the star at the bottom of the animation. And you can see that that's going to change the way that we see the variability of the star. If you're looking top down on the spinning star, you don't see spots come and go. The same spots are always visible. So the brightness doesn't change very much. But if the system is viewed on the equator, then you see larger variations. And so we actually can see for groups of stars that are about the same age, and therefore we think they have the same spot coverage, that some of them have big spot variability and other ones have small spot variability. And that probably has to do partly with the stellar inclination, the orientation that we're viewing it at. So for more examples, here are 2 more spotted stars. On the left, we have K2 and TESS photometry, of two different stars. And so this is from the Kepler mission on top, after the Kepler mission technically died and then they brought it back, and the test mission on the bottom. And you can see again that there's this roughly sinusoidal variability of the stars that is roughly 1% in amplitude, that varies on a timescale of a few days. This is from a paper that I published this year where we tried to infer the spot coverage on these stars using an ensemble fitting technique, where we looked at groups of stars that have the same age and then tried to marginalize over the fact that we don't know the inclinations of the stars in order to figure out how spotted they are. And so we've recovered maps that look like the maps on the right. Now, why am I telling you all of this? I'm telling you all of this because there are some things that we want to be able to measure about star spots. One is differential rotation, and the other is spot evolution. We know that star spots, if they behave like the sun's spots, will emerge and decay on some timescale. We know that there are some exceptions to that in the stellar astrophysics world. We also expect that stars don't rotate as a solid body. And so if you look at the surface of the sun and you actually measure how quickly sunspots are moving around on the surface, you find that sunspots move fastest at the solar equator and slower near the poles. And we call that differential rotation. What drives it is really complicated, and Andreas might be more qualified than me to describe it. But differential rotation, we believe, is a fundamental property of stellar atmospheres that should occur on other sun-like stars as well. But it's been really, really difficult to tease out of real light curves. And I'm going to try to show you why. If any of this is confusing, stop me right away because I want to make sure that it's clear. What I'm showing you now is, let's focus on the top left plot first. Imagine you have...
Brett?
Yes?
May I add just something?
Of course.
About differential rotation.
Yes.
Differential rotation is also in this moment considered to be the single most important source of energy for anything that has to do with solar magnetism. And we don't know if that's true for stars.
Thank you.
But it is, without being able to measure, it has never been measured at the scale at which we would like to measure it. And that's kind of like the goal of our challenge, to measure something that is kind of like a holy grail of our understanding of stellar magnetism.
Yes, I should have highlighted that a little bit more. We know that differential rotation is the key ingredient in models of stellar dynamos that produces the stellar magnetism we see expressed on their surfaces. And so if we are to understand how the dynamo works, where the dynamo here is defined as the series of physical mechanisms that produce stellar magnetism, we want to be able to figure out how differential rotation works and why it works and how it varies from star to star. Are there any other questions here? All right, great. So in this plot on the upper left, what I'm showing you is what a star would look like if the star was rotating and we were viewing the star from its equator. And as you looked at the star as it rotates, it has two spots on it. One spot is at a low latitude, like near the equator, and the other spot is at a slightly higher latitude, like say 40 degrees. Because they're at different latitudes, the two spots are actually rotating around the star with slightly different speeds. And so that you can see reflected in the light curve that I'm showing you, which is the contribution of each spot on a light curve of a rotating star in the blue and the orange. And you can see that the orange one has a short pulse downwards, and then it comes back up, just like the blue one. But the orange one's period is slightly longer than the period of the blue one. And that, in this model, is arising just from the fact that the spots are at slightly different latitudes and the star is rotating slightly faster at the equator than it is at the higher latitude. If you were to add these two contributions together, you would get the lower left plot, which shows the kind of beat pattern, you might say, if you were a signal processing nerd like I am, that emerges from the slightly different periods of the two rotating spots. Separately, on the right side, we have a different effect that causes a similar looking light curve phenomenon, which is spots emerge and decay with a timescale of about a month on a sun-like star. I've envisioned here a star that has a spot lifetime of, say, about 100 days. And you can see in the blue dashed line in the upper right plot what the envelope of this curve is doing. The spot is emerging, it's getting bigger, and then it's decaying, it's getting smaller. And its effect on the light curve overall looks just like the beat pattern from the contribution of two individual spots on the left, but is just arising from the fact that the spot is evolving, which is what we see on the right. So this is meant to show you that even if you had zero noise, if you had perfect observations, it would be a little bit difficult to distinguish between one and the other. You could say at the time of 100 days, the dip is slightly wider than it is at the time of 100 days on the right, but it turns out that as soon as you add noise to your observations, these light curves look identical to one another. So it's really hard to split apart these two effects. And then it's even harder because real spots have lifetimes similar to the rotation period of the star. In the example I just showed you a moment ago, the star spots last many rotations. So you can see their signal and you can really envision the pattern that it's going to produce. But now let's take that same example and let's give the star spots finite lifetimes that are similar to the rotation period. And what you'll see is, again, with one spot on the left, the envelope of the curve is in the dashed line, and that's the spot emerging and decaying. And the solid line is showing you what the light curve contribution is from the individual spot. It produces this double dipped feature, which is all we can really hope to see on a sun-like star. And then on the right is an example with two spots where the spots are at slightly different latitudes. That will give us the signal of differential rotation that we're looking for, but it's only going to last one period. So how do you measure something that's varying on the timescale of its period? That's one of the challenges that we're going to try to overcome in this problem. So just to summarize some of the things that I've mentioned, I'm going to stop here. There's a periodic signal that we want to measure, but it lasts one cycle. And a lot of the classical techniques that astronomers are used to using build up signal by looking at periods phase folded on top of one another. And we can't really do that in this exercise. Another problem is that spots are evolving at the same time as they are rotating differentially. And so the competing similar signals from both effects are going to be difficult to distinguish in real observations. And then to add one other wrinkle, we don't know the orientations of the stars that we're looking at. We can make assumptions, and there are observations we can take, but for the vast majority of the stars, for example, in the Kepler field, we don't know what their orientations are. So these are some of the challenges that we're going to be thinking about and hopefully overcoming over the course of the next few weeks. Are there any questions here?
I have a question.
Yeah.
Do we really know cases of stars where the star spots, like you can see two cycles of spots within one period, or more than two periods within one stellar rotation?
I'm not sure that I understand. So are you saying there are, sorry, go ahead.
You're saying that the lifetime of the star spot is about the same as the life as the time for the rotation, right? So you're seeing on average one star spot per rotation, and that's a problem. One period.
That's right. That's right on sun-like stars. There are other examples, like some of the stars that I showed in this example, where the stars are much younger and have more spots. and those spots last longer. So I showed you some exceptions that are nice, neat examples that make for clean slides. Because if I were to show you an example that looked like the sun looks, you wouldn't see nearly anything because the signal is very small.
Okay.
Does that answer your question?
Yes.
Okay,
Yes.
great.
If I may add, yes, the rotation period of some stars is very fast compared to the decay of the spot. So there are potentially stars in our sample where we can see the beat. So there are stars like the sun where the rotation is slow, it lasts the same as the duration of it. So we will see curves. Everything that Brett has shown is something that we could potentially see in any combination in some way. And it's like a massively degenerate problem where what we're trying to do is, go from those curves to the rotational properties of the star, which is, and the evolution of their spots. So does it last long? We don't know either if spots in stars last like in the sun. In the sun is about a month-long lifetime, give or take. But that may not be true for stars either. And so that's another thing that we would like to mention.
Thanks.
Question, I suppose. So I think one thing you didn't mention about like the challenge is that we're specifically focusing on stars that have exoplanet transits, right? Is that true?
Andres,
We have not decided that. Yeah, we have not decided that. So I think that we will talk about next week about the process that we will do to really like specify exactly what we're tackling, the data space that we will work with, and so on and so forth, on the first week of the FDL. So we could focus on stars with exoplanet transits alone, or we could try to do all of them, or we could try to do both of them in parallel. This is something that we will all design together. So all the specifics are not yet solid in stone.
And just for the others who don't know what Daniel's talking about, Daniel's referring to the fact that there are planets orbiting probably most of these stars. And for a subset of the stars for which we've discovered the planets, when the planet passes between the star and the Earth, we get an eclipse. And during that eclipse, you can break a lot of degeneracies. You can figure out precisely what the brightness is across the surface of the star beneath the exoplanet, because the exoplanet kind of removes a bit of stellar brightness that is dependent on the position of the planet. And so you can kind of use it like a stethoscope and figure out what the pulse of the star is underneath the planet as it scans over its surface. And so I did my PhD on that. That's what I did. And so I love that technique. I can talk about it until I'm blue in the face, and I'm going to try not to right now, other than to say that it is this magical opportunity that eclipses afford us that break a lot of degeneracies. And so there is a chance that we will be using transiting exoplanets to try to break some of these degeneracies. And I think that's probably all I can say, right? For now, we're keeping the project open.
We will devote an entire week to really ironing out all these details.
Mm-hmm.
All right, cool, thank you. So before we move on to the last thing that we wanted to discuss today, I just wanted to quickly see if Tansu wants to say hi because he joined throughout the presentation.
Sorry, I couldn't unmute myself. Hello, everyone. So this is Tansu. I joined kind of late, as I'm the last researchers to join the team. So I couldn't open my camera because I'm in a hospital setting right now, but kind of trying to just catch up with the talk. Thanks a lot for all the details. This is kind of a science that I'm tangentially interested, but I only work on exoplanets, so differential stellar rotation is very interesting. I would certainly be very interested to keep the analysis or science-focused exoplanet related if possible, because I think the problem definition actually included exoplanets, but obviously that's something to discuss in the future as well. But thanks for the talk. Hi to everyone.
Yeah, thank you. Great. So as Andres has mentioned, we have a very specific methodology on how we iron out all of these details that makes sure that we are all on the same playing field, regardless of the amount of background that you guys are starting with. And we don't want to spend a whole lot of time talking about it today because we're almost out of time and we want to be mindful to let people go on time. But the two things that we will likely schedule next week is one meeting to start playing around with some of the tools that we're going to be using over the course of the summer. And then in addition, we want to introduce the methodology of the sprint a little bit more to you guys to give you a bit of a better expectation, like a bit of sense of what to expect in that first week. And that will help iron out a lot of these details. And then you guys are all set up and ready to go to start tackle the problem. But what we wanted to do today is when we had the one-on-one meetings with you guys, we tried to get a sense for what your normal working schedules are like. And so we tried to put a tentative schedule together just to give you an idea on how collaboration across so many time zones might work. So I'm going to share my screen really briefly just to give you a little bit of an idea of what that will look like. And it looks really scary now because it has all of the different time zones in it. And I'm purposely starting on week 2 because week 1 will be entirely dedicated to the sprint. But basically what I wanted to show you is something that we talked about in the one